So far we've proven several theorems about prime numbers. In particular, we've proven that every composite number has a prime factorization. If p is prime and p divides a product, then p must divide one of the factors. And these allow us to prove the fundamental theorem of arithmetic. Every integer greater than 1 can be expressed uniquely as a product of prime numbers up to the order of the factors. For example, let's show that 30 has a unique prime factorization. So first of all, we note the importance of specifying a prime factorization, since we can write 30 as a product of composite numbers in many different ways. So our theorem guarantees that we can find a prime factorization of 30, which will be Now to show something is unique, assume there's another. So suppose there is some other prime factorization of 30. So our two products of primes must be equal. Now note that this means 2 has to divide the product on the left-hand side. And since 2 is prime, it must divide one of the pi's. But since all of these are prime, this means at least one of them must be equal to 2. And by a similar argument, one of them must be 3, and another must be 5. Since the indexing is arbitrary, we can simply make these the first 3 pi's. And so we can rewrite the left-hand side, reindexing as necessary, as the product. And removing the common factors, we get. But the only way for a product of integers to equal 1 is for all of them to be 1. Since the pi's are supposed to be prime, and by definition 1 isn't prime, this means that p4 prime and so on can't exist. So any prime factorization of 30 must contain a 2, 3, 5, and no other primes. It's worth noting that this also motivates why we don't want to consider 1 to be prime. If we did, then 30 could have any number of prime factorizations, differing by how many factors of 1 we include. We already proved that every composite number has some prime factorization, so we want to prove that the factorization is unique, and we'll generalize what we did with the factorization of 30. So again, suppose n has 2 prime factorizations where the pi's and the qj's are primes, and so they have to be equal. And again, our prime p1 divides the product, and so it has to divide one of them. And again, by reordering, we can assume that p1 is q1 and remove the common factor. Now lather, rinse, repeat. We can't exhaust one side without simultaneously exhausting the other, since that would give us a product equal to 1. So both sides must have the same number of primes, appearing the same number of times, and that proves our theorem. The significance of the fundamental theorem of arithmetic is that it gives us a unique recipe for every number. And what this means is that if we ever need to compare two numbers, we can look at their recipe. For example, compare this product with this product. Now we could multiply it out, but we don't want to. On the other hand, if we take a look at the prime factorization, a prime factorization of the first number will be a prime factorization of the second number will be, and since the prime factorizations are different, the two numbers are different.